Hello, this is an extra bit for my PCubed portfolio because I've been fiddling with the gamma function and I've come up with a nice proof for the Euler Reflection formula, which, it's not entirely complete because it kind of leaves a bit out at the end, which I'm still working on, but yeah, that's what I'm going to do. It's fun and I enjoyed proving it, so I wanted to create a little video to put on the end of the portfolio or put in some sort of appendix, because typing this up in LaTeX would have been a pain. So this is what we're going to try and prove. We're proving that gamma of z times gamma of 1 minus z is equal to pi over sine pi z. Obviously, as I said, at the end, we're going to do a bit of fiddling and make sure, well, the last bit's assumed, basically, but we do enough of the proof to make it worthwhile showing. So we can first write the gamma of 1 minus z, which would be the integral from 0 to infinity of x to the 1 minus z minus 1 e to the negative x dx, which is just the integral of x to the minus z e to the negative x dx. So that implies the gamma of z, gamma of 1 minus z, is the double integral from 0 to infinity of x to the, well, we're going to put x to the 1 minus z minus 1 e to the negative x dx. Doesn't matter. We can then put alpha to the minus z e to the negative alpha d alpha, and then fiddle a bit. So we've got x to the z minus 1, then alpha to the minus z, and then we've got e to the negative x plus alpha dx d alpha. I don't know if I'm covering anything, but no. And then we can put in a couple of substitutions. Well, probably want to do one more step to make it obvious what the substitution is going to be. Then, because that's negative x, we can put 1 over x, then x over alpha to the z. That's the same as that, because that's just 1 over alpha to the z. That's x times, well, 1 over x times x to the z. So then you can take x to the z over alpha to z, bring out the 1 over x, and then take out the alpha, dx d alpha. And now we're going to put in some substitutions. Doesn't really matter what we call them. I'm going to call them beta is x plus alpha, and gamma is x over alpha. But because we've got a double integral, we have to do the Jacobian. So we take our Jacobian. So that would be the beta x, the gamma x over the beta, oh, is that z? No, alpha. The beta alpha, the gamma alpha. But we haven't got these in terms of alphas and betas yet. They're all, well, you have to get them in terms of x and alpha, sorry, and we haven't done that yet. So we're going to quickly say that we know that alpha gamma is x, so beta must be alpha gamma plus alpha, which is alpha 1 plus gamma, which implies that alpha is beta over 1 plus gamma. And then we know that alpha is x over gamma, so do the same thing. Beta is x plus x over gamma, which is x times 1 plus 1 over gamma, which is beta, which implies beta gamma over 1 plus gamma is x. So then we can take our Jacobian and evaluate it. So taking the derivative of x in terms of beta is gamma over 1 plus gamma. Then taking x in terms of gamma, which is a bit complicated, but we're just going to use the chain rule. So that's going to be beta over 1 plus gamma minus beta gamma over 1 plus gamma all squared. Yeah, my writing's gone. And then we're going to take alpha, which is this one here. No. Is it here? No, it's this one here. Take this one here and differentiate it in terms of beta, which will be just 1 over gamma. And then differentiate it in terms of alpha. Sorry, alpha. I said alpha, I meant gamma. Get myself confused. Shouldn't use Greek letters. And then we're going to times them together. To find the determinant, which would be 1 plus gamma to the third. And then times these two together. So it'll be beta. Just take the beta out. And then you just go 1 over 1 plus squared minus gamma over 1 plus gamma to the 3. These two terms are the same, so they cancel. So you end up with beta over 1 plus gamma all squared. Alright? I'll negative that. That makes sense. Then we go back to our integral, call it I. I is then dealing with the limits when alpha is at infinity, beta is at infinity, and also, well, we've got a bit of a fiddling here. So this one goes from 0 to infinity, but this one goes from infinity to 0. But we've got a negative, so we pull that out and rejiggle it. So we've got 1 on x, we've already got x's here, so it's 1 plus gamma over beta gamma. And then this one is x over alpha, which we've got here, which is gamma to the z. And then e to the negative x plus alpha, which is beta. Then d beta, d gamma. Which then, oops, we haven't put in here, sorry. We won't put the beta over 1 plus gamma all squared minus. But then we've got, and just take that minus here and plug it into there, and then we can piddle with the limits. So then we get 1 plus, well, which then that, and then gamma to the z, e to the negative beta, d gamma, which then is 0 to infinity, 0 to infinity. Get ready for our second substitution. Oops, we're going off the paper. That's unfortunate. Right, there. Which then we've got gamma to the z minus 1 over 1 plus gamma, and then e to the negative beta, de gamma. In the original filming I had a bit of a moment at this point, so we shall go back to this step and we shall solve this integral from here. At this point we will take the e to the negative beta onto this side and split the integral back into two integrals. Okay, so then this is negative e to the negative beta between 0 and infinity, then 0 to infinity of gamma to the z negative 1 of 1 plus gamma to gamma. This will go to 1, and then we'll end up with from 0 to infinity of gamma to the z negative 1 over 1 plus gamma to gamma, which then we shall split from 0 to 1 of gamma to the z negative 1 over 1 plus gamma to gamma, plus 1 to infinity of gamma to the z negative 1 over 1 plus gamma to gamma. At this point, we're going to introduce a substitution. We'll let gamma equal 1 over t. So that implies that the gamma beta t equals negative 1 over t squared. So when we plug this into, well, we'll leave this integral alone because you'll see in a minute what happens to the bounds. And then we'll plug in the substitution, dealing with the bounds. That'll go from 1, and 1 over infinity is 0. So then we have the 1 over t z negative 1 all over 1 plus 1 over t, and then you've got negative 1 over t squared dt. And now moving the camera slightly, or even better, move the paper upwards. Sorry, I had to move the camera. And then we go from 0 to 1 of gamma to z negative 1 over 1 plus gamma to gamma. And then you can, because of that negative there, you can swap the limits and then put in the 1 over t. So you've got 1 over t to the z over 1 plus 1, or t plus 1 to t, which is then, you can just 0 to 1 of gamma to the z negative 1 over 1 plus gamma to gamma plus the integral from 0 to 1 of t to the negative z all over 1 plus t dt. And now going back over here, we can, because they've got the same limits, we can let these integrals be the same thing. We'll just change the variable, because the variable doesn't matter, to s. So that's s to the z minus 1 plus s to the negative z all over 1 plus s ds. But we know that 1 over 1 plus s is equal to the sum between k equals 1 and infinity, or even k equals 0, it doesn't matter, of negative s to the kth power. So then we can pull all this in there. So you end up with the integral from 0 to 1 of the summation from k equals 0 to infinity of negative s to the k, or you can put s to the k times negative 1 to the k of s to the z negative 1 plus s to the negative z. Then you can take that and you can swap by Fubini theorem the summation sign and the integral. So that's the summation from k equals 0 to infinity of the integral of, I'll put negative 1 to the k out here, of s to the k plus z negative 1. Oh, got my ds. I've got my ds over here as well. And then plus the s to the negative k plus z. Oh, sorry, I've had a moment. Negative k plus z. And have I done that? I've done that incorrectly. Yeah, s to the z, negative z plus k. And then you can take the s, take the integral of that, which is the summation from k equals 0 to infinity of 1 over k plus z of s to the k plus z, and then 1 over 1 plus k negative z of s to the 1 negative k, 1 positive k negative z between 0 and 1, which is then equal to the summation from k equals 0 to infinity, oops, having a problem with the paper, of, then you plug in 1 to this, which will just come out as 1 over k plus z plus 1 over 1 plus k negative z, and then plug in 0, which will then go to 0. So this is the summation, which is then equal to the pi over sine pi z. Proof complete.